Section 8.2 is on an integration technique called integration by parts. So integration by parts is sort of the backwards of the product rule. It's the analogous version of it for integration. And this first slide really gets into kind of a derivation of where the formula comes from. I don't want to spend a lot of time on this, but I do want to remind you that the product rule, when you're taking the derivative of two functions that are being multiplied, remember that we say it's the derivative of the first function. In this, the way this is written would be du dx times the second recopied, which is v, plus the derivative of the second function times the first recopied. And I'm going to skip the details here, but on this slide they show you where our formula comes from, but I want to get to the main point here, which is this rule right here. This is the formula we apply when we're integrating by parts. When do we use integration by parts? If we are taking the integral of two functions that are being multiplied together. So if we think of those two functions as u and dv, that's the important thing. You want to establish which one's u and which one's dv. The antiderivative of that would be u times v minus the integral of v du. And this sounds a little complicated at first, but once we do a few of these, you'll get the hang of it. It isn't actually too bad. So this is the formula again, just rewritten. U is what usually, if we can choose the function for u, if we have two of them up there to choose from, if u differentiates down to 0, that's helpful. So we'll talk about in a minute how you want to choose u. You want dv to be something that's fairly easy to integrate. So this is sort of the backwards version of the product rule for integration. The way we choose u, though, I like this little acronym. It's called LIPIT, and it's a little acronym, and it stands for the different types of functions we might encounter. And so this is sort of the hierarchy in which you would use to choose u if you have these in the function. L stands for logs. So if you have a log, that's your first choice for u. If you don't have a log, check to see if you have an inverse trig. That would be the next choice for u. If you don't have u, check, or if you don't have an inverse trig, check to see if you have a polynomial. If that's not there, check to see if you have an exponential function, and then finally check to see if you have a trig function. That's your last choice for u. So let's do an example here. We have the integral of x times the cosine of x dx. So the first clue that we're even using integration by parts is that we're multiplying two functions together. That's the first thing you want to notice. And then you want to look at, okay, what are those two functions? In this case, x and cosine x are the two functions. And then you want to decide what to use for u. So if you go back to that LIPIT rule, we have a polynomial, right? X is a polynomial, and we have cosine x is a trig function. Let me go back for just a second. So polynomial is your first choice for u before a trig function. So in this example, I'm going to let u equal the polynomial factor, which is x. And that means that whatever else is in there has to be dv. So dv is the other function, cosine x, and I always keep the dx with the dv expression. So to use this formula, I need four things. I need u, v, and then I need v and du. So u we know is x. So du would be dx, right? The derivative of x is 1, so du would be dx. And then I need v, which would be the integral of dv. So dv represents the derivative of v. So to get v, I need to go backwards to get the integral of v, which would be sine x, because sine is the antiderivative for cosine x. So we're going to put it together in our formula. So we've got u, which is x, times v, which is sine x, minus the integral of v du. So the integral of sine x dx. And then that we can integrate, so we're going to have to integrate again, but this is something we can handle. The antiderivative of sine x would be negative cosine x. So because of this minus sign, that became a positive cosine x. And that's your antiderivative for the original function. Okay? Let's try this one, the antiderivative of the natural log of x dx. So at first glance, it looks like, okay, maybe this is an integration by parts because I don't see two functions that are being multiplied together. However, we can think of it as integration by parts if we think of one of the functions that we're multiplying as just 1. So natural log of x is one of our functions, and 1 is going to be the other function. So if you think about your LIPIT rule, L is log, stands for log. Of course, we have a natural log of x, so that's what we're going to use for our u. The other function, dv, then, would have to be just 1. So dv would be 1 and then I keep the dx with my dv every time. So then I need du, which is 1 over x dx, the derivative of the natural log, and then I need v, which is the antiderivative of 1 dx, which would just be x. So we put this together, we have u times v, so the natural log of x times x, minus the integral of v, which is x, times du, which is 1 over x dx. Notice that those x's cancel out, and I'm just left with integrating 1 dx, which is just x. So that expression is the antiderivative for the natural log of x dx. The idea is this thing that you're integrating here should be something that you can work with. So for example, the integral of 1, of course, we can figure that out. Let's try this one. We've got the antiderivative of e to the x times cosine x dx. So think about Lipit again. Which one is going to be your choice for u? Is that going to be the trig function or the exponential function? Well, e comes before trig in this acronym, so u is going to be e to the x. That means cosine x dx has to be dv. And so du is equal to e to the x dx, the derivative, of course, of e to the x. Antiderivative of cosine x is going to give us our v, and that would be sine x. So we're going to put this together. So we have e to the x, uv is e to the x times sine x, minus v du, which is sine x times e to the x dx. Now you notice this is not so easy to integrate. This is integration by parts again. So we're going to repeat the process, and we're going to let u equal e to the x. dv, of course, is sine x dx, so I'm integrating this little integral right here. So the derivative, du, is e to the x, and v is negative cosine x this time. So make sure you see what's going on. This expression is the original uv that I had. Now I'm integrating this function. So the integral of sine x e to the x is going to be u times v for my new substitutions over here, minus the integral of v du. Now you may notice there's a little bit of a pattern here. I'm going to keep going all day because neither cosine or e to the x will ever differentiate down to 0. So I'm going to just kind of keep in this cycle if I keep doing this. So the way we're going to handle this is we're going to set up an equation. And let me show you what I mean. First of all, I clean this up a little bit is all I've done here. This negative in front of the original integral had to be distributed. So this first term becomes positive. The second term, we were subtracting a negative, which made it positive, but then the negative in front made that integral negative. So pause for a second and think about this. This entire expression is equal to, remember, the original antiderivative. And you notice that I stopped doing this process when I got to an integrand that was equal to the original one that I started with. So what I'm doing is I'm setting this equal to the original integrand that I started with. And we're literally going to think about solving an equation here. Because I have two integrands on each side that are the same, I'm going to take the one on this right side and I'm going to add it over to the other side. So that gives me 2 of those integrands, e to the x cosine x. So I'm trying to solve for the integrand of e to the x cosine x, so I just need to isolate this by dividing by 2. And so there's my antiderivative. Sorry, that's kind of hard to see. There's my antiderivative. E to the x sine x plus e to the x cosine x all over 2 plus c. So this is a cyclic pattern, and this will work whenever you have an integrand. Usually it's going to involve a trig function and an exponential function with this pattern. But this idea of setting up this equation is real common when you have a cyclic pattern like this. And again, how do you know when to stop? When you get down to an integral that matches the original integrand you started with. You're going to stop and set up the equation. Another way of doing integration by parts, and I'll tell you when we meet in the office, this is actually how I usually do these. It's an application of the formula but using a table. So this is called the tabular method. I like the tabular method, and the tabular method, despite what some textbooks say, can actually be used in every situation, even when it's cyclic, like that last one we just saw. So I'm going to show you some examples here, and then when we meet in the office, we'll talk about using the tabular method again, anytime you have an integration by parts problem. It's the same formula. We're still going to choose u, and we're still going to choose dv the same way we've been doing. It's just sort of a visual way of applying the formula. So I'm looking at the integrand of x squared times e to the x. So first decide your choice for u. U is going to be the polynomial in this case, which is x squared. So that means dv is going to be the e to the x dx. So on my paper, I'm going to set up a table with two columns. The first column is u, and then it's going to be followed by all of its successive derivatives. The second column is dv, and it's going to be followed by all of its successive integrals. So you're going to start by writing down your choice of u, and then what you're going to do is you're going to differentiate that. If you can differentiate it down to 0, go ahead and do that. So if u is x squared, the derivative is 2x, the derivative of that is 2, the derivative of that is 0. So now I'm done because I've got something down to 0 here. My dv, of course, is e to the x dx. My integral is e to the x. Integral of that is e to the x. Integral of that is e to the x. So I'm stopping in the fourth row because that's where I stopped in the first column. And then I'm going to alternate signs. So I'm going to do plus for the first row, minus, plus, minus. And then I'm going to integrate down the diagonal. So I'm going to draw a diagonal for the first part of the formula, basically, is x squared times e to the x minus 2x times e to the x plus 2e to the x. And then you stop and the last row you integrate going across. Well, the integral of 0, because 0 times e to the x, of course, is 0, would be a constant c. So there's your plus c at the end. And this looks complicated, but I promise once we do a few of these, you'll get the hang of it. But this tabular method is usually faster, and so this is generally the way I do this. If we have to do repeated integration by parts, this is always a better way to do it. If we had done this the other way, don't write this down, but just watch. We chose our choice of u, and we chose our choice of dv. We apply the formula, and we get another function that we have to integrate, so we have to do integration by parts again. We apply the formula, we get another function we have to integrate. Doesn't require integration by parts this time, but there it is. So really, I'll leave it up to you which method you prefer, but I prefer the tabular method, and that's what I'm going to use from here on out. Nearly all integration, I almost would say all integration by parts. I'm about nearly, I would dare to say all integration by parts problems can be done using this tabular method, even if one of them doesn't differentiate down to 0 like it did in that last question. So let's do an example of one that's cyclic. So we've got the integral of e to the x times the cosine of 3x. So I'm going to choose u and I'm going to choose dv, still following the Lippitt rule. So u would go with the exponential function, so that's e to the x. Now I'm going to stop here and I'm going to put the dv because e to the x doesn't just differentiate down to 0. The derivative would be e to the x all day long. So I'll show you where to stop the table in just a second. We've got e to the x is u. That means dv has to be cosine of 3x. So I'm going to go one row at a time. The derivative of e to the x is e to the x. Remember over here you have to integrate or get the antiderivative of cosine of 3x. So if we do a little mini u substitution and let u equal 3x, we'll see the antiderivative of that is 1/3 sine of 3x. How do I know when to stop my table? Well, remember earlier we set up that equation when it was cyclic, when we got to an integrand that matched the original integrand. So if you're using the tabular method, what you want is your row going across to match the original integrand. So if I go again, I get e to the x for the first column, and then antiderivative of 1/3 sine of 3x will be negative 1/9 cosine of 3x. The 1/9 is a coefficient, so don't worry about that. But notice if I go across, e to the x times cosine of 3x is the original integrand. So that's where I'm going to stop. So now I'm going to alternate signs, plus, minus, plus. I'm going to go down the diagonal. So the first part of my antiderivative is 1/3 e to the x times sine of 3x minus, it's minus and then a negative 1/9. So plus again, 1/9 e to the x cosine of 3x. And then when you go across, that's your integral. So then it's minus, because of this negative sign, the integral of 1/9 e to the x cosine of 3x. So here's what I just had. This was at the bottom. Just wrote it up here again so we can see it. So here's where I'm at. Think about what we did earlier with the equation. If I am trying to get e to the x cosine of 3x, the antiderivative, I'm trying to get that by itself. I have it on both sides of the equation. So this integrand, I'm going to add to the other side. When I add the 1/9, there's a coefficient of 1 in front of this integrand. So when I get a common denominator, that gives me a coefficient of 10/9. Now I need to solve for this integrand, which means I'm going to divide by 10/9 or multiply by the reciprocal 9/10. When I simplify it, I get this expression right here, and that's your antiderivative. So when did we stop the table? The thing to remember on a problem that's cyclic like that is you stop the table when you get to where, let me go back real quick, when you get to the step where the two u and the dv are the same as what you started. And that's when you're going to stop and set up your equation and do what we did earlier. Let's try this one, the antiderivative of arctangent x dx. Notice this isn't one we've done before. We've done the antiderivative of 1 over 1 plus x squared is arctangent, but we haven't actually integrated arctangent. So again, it may not look like an integration by parts problem, but remember, we can think of the second function as 1. The second function is being multiplied as 1. So u, of course, would be the inverse trig function if we follow Lippitt, and then 1, or just dx, would be the dv. All right, so I'm going to do one row at a time. So the derivative of arctangent of x is 1 over 1 plus x squared. The antiderivative dx would be x. Now, this is not going to be cyclic like the last problem. How do I know when I'm done? How do I know when I stop my table? When you get to a row that if you go across, you can find an antiderivative for it. And you'll notice right here, if I go across x times 1 over 1 plus x squared, that would be x over 1 plus x squared. I can integrate that using a u substitution. So I'm going to stop my table after the second row. So we're going to go down the diagonal. Notice I alternated signs again. So, and then we're going to go across, and that last row is going to be the integral. So we're going to have x times arctangent of x minus the integral of x over 1 plus x squared. And if we do a u substitution on that, let u equal the denominator. That means we have a 1/2 in the front. And then we have 1 over u inside the integrand. And so that we can integrate using a natural log. So we have x times arctangent of x minus 1/2 times the natural log of 1 plus x squared.